Mathematical preliminaries for multivariable optimization. We have a bunch of different topics to get through before we can even get into optimizations, and all this will tie into the various methods that we discuss. Multivariable functions. Let's talk about a multivariable function and the notation that we are using. So we have some function that's a function of a bunch of different variables, and we're going to list those variables as x1, x2, all the way up to xn. So there's sort of n variables that f is a function of. And we can store all of those variables in an array, a one-dimensional column vector. And for compact notation, we will write this as a lowercase x. So if we apply this function with all of these input variables, we'll just write that as f of a function of this lowercase bolded x. So here's some examples. Just some sort of function x plus y plus x times y. Our two variables that f is a function of is x and y. Now look at some kind of Gaussian that has an amplitude and a width. And it's also a function of x. So there's three variables that this is a function of. So we would list all of them and still call that lowercase bolded x. And then f of that lowercase bolded x really is this, a times the exponential of minus x over sigma squared. Scalar and vector fields. First, let's talk about a scalar field. By field, if we're thinking about electromagnetics, certainly the electromagnetic fields are fields, but in a purely mathematical sense, a field is just a function of usually more than one variable. So we're showing a picture here of a function that's a function here of two variables, x and y, and it kind of looks like a cloud. It's a scalar field where there's just one number at every position, and that one number would represent a magnitude. So think of a cloud, and the density of the cloud is a scalar function. There are also vector fields or vector functions. Now there's a vector at every point in space if we're talking about x and y. So vector fields have both a magnitude and a direction. So part of them is a scalar field, but another part is also direction. So very often they're written something like this, and the magnitude of the arrows conveys the magnitude, and of course the direction of the arrow conveys direction. So scalar and vector fields. Vector fields contain twice as much information as a scalar field. Isocontour lines. Here we're looking at a scalar field, and if we think of this scalar field, let's say as elevation, if we were to walk a path that does not go up or down, but just stays at the same elevation, that's an isocontour line. And if you're used to reading maps where the isocontour lines are the more closely spaced, that indicates where the elevation is changing most rapidly. Gradient of a scalar field. So we start with our scalar field. Now, if we calculate a gradient, that is pointing uphill, but it is not a smart function. And again, imagine you're standing on a very hilly terrain. The direction of up is not from where you are towards the highest peak. That would take too much intelligence. Instead, imagine you're just staring at your feet and you look at which way's up just immediately where you're standing. That's the gradient. So for example, over here, up is in this upper left direction, even though the absolute peak is way down here. The gradient isn't smart enough to note a point here. The gradient points up based on what is the steepest up right where of that point of interest is. So that's the gradient of a scalar field. Now there's a nice relationship between the gradient and the isocontours. The gradient is always perpendicular to the isocontours. That makes sense. If the gradient is always pointing in the direction of maximum change and the isocontour is in the direction of no change, it makes sense that those would be perpendicular to each other. Gradient and Hessians. The multidimensional gradient. We would like to write the gradient for more than just x, y, z. And we can get this if we look at the gradient in x, just x, y, and z. So the gradient of our scalar function f, which is a function of x, y, and z, that is the partial derivative of that scalar function with respect to x in the x direction, plus the partial derivative of that scalar function with respect to y in the y direction, plus the partial derivative of the scalar function with respect to z in the z direction. So you see the pattern here, and we can generalize this now to any number of dimensions. So rather than write x, y, z and then be confused of what comes after, let's just write x1, x2, x3, all the way up to however many dimensions we have. And we store all these in a column vector that for compact notation we will write as a lowercase bolded x. Now the gradient of a scalar function of all of these different dimensions is written this way. The partial derivative of the scalar function with respect to x1, and when it's in this first position, that means it's in the x1 direction. Then we have the partial derivative of the scalar function with respect to x2. It's in the second position, that's the x2 direction, and so on. And we can do this for any number of dimensions. So that's the multidimensional gradient. Properties of the gradient. First, we could say that it only makes sense to calculate the gradient of a scalar field. Now, for those that are sticklers for details and maybe rigorous mathematicians, they might say, oh, well, you know what? There is actually a gradient of a vector field. And that's actually a tensor quantity. It's called the Jacobian, and that's really outside the scope of this course. So in this course, we're going to say that it really only makes sense to talk about the gradient of a scalar field. The gradient points in the direction of maximum rate of change of that scalar function. So if it's elevation, the gradient points up. The gradient is perpendicular to those isocontours. And the gradient always points up. It points towards the bigger positive numbers. So if we have a gradient and here's the big positive numbers, the gradient is always pointing towards increasing values. And if we have a linearly changing sort of function, again, it's pointing towards the bigger numbers always. Sometimes we don't have an analytical expression for that scalar function. Maybe that function's coming out of a simulation or something else where there's just no equation and we don't have a closed form equation, no closed form derivatives. Now we have to resort to a numerical calculation of the gradient. So let's just look at the first one. The partial derivative of our scalar function with respect to x1, well, it's our function at x1, but we're adding a small little delta to that x1. And of course, it's all the other variables too, but for compactness, I'm not writing them, but we're adding some small increment to x1 minus that function value at x1, but that x1 is minus some little increment delta 1. So the span between these two f values is 2 delta 1. So this is actually the slope. And this is the difference in f's, that's the rise, and the run, the distance between them is 2 delta 1. So this is actually a finite difference approximation for a first order derivative. And we do that for all of our dimensions, and now we are numerically calculating the gradient. Now, this scalar function is probably a simulation or something much more calculating, or something much more complicated, I mean. And so it can take a very long time to evaluate, and that's the cost you pay sometimes when you're doing this numerically. It may take a very long time. Let's think about our derivative tests now that we have multiple dimensions. So let's have a scalar function f of xy, and we check the first order derivatives in both x and y, they equal 0, and we check the second order derivative, they're both less than 0. Does this mean we have a minimum? From what we've discussed so far, it sort of does. However, the answer is no. And there's something called a saddle point. And think about the shape of this surface, roughly the shape of a saddle that you'd put on a horse to ride it. And if we look at a projection this way, we look at the minimum here along the x-axis, we end up here. So the first order derivative is 0, the second order derivative is less than 1, indicating it's a minimum. If we look along the y direction, again, the first order derivative is 0, second order derivative is less than 1. That indicates a minimum. One would think that that is a minimum. However, if we look at a projection along y equals x, that's actually going up in the middle. We actually have a maximum along that direction. Well, that implies we don't have a global extrema here. That is a saddle point. So our derivative tests, as we've learned, are only for one-dimensional functions, and we have to reconsider this now when we have multiple dimensions. We will need the Hessian. The Hessian is something that roughly describes curvature when we have multiple variable functions. Now, this makes less sense, let's say, when we have a six-dimensional space. But if you can imagine curvature of a six-dimensional space, I can't. That's what the Hessian is doing. And so we're going to use the Hessian to determine whether we have a maximum or a minimum. So we define the Hessian this way, and that's pretty crazy. So let's look at this for 2 dimensions. So the 2-dimensional Hessian, we have the second order derivative of f with respect to x in the upper left quadrant. And the lower right, we have the second order derivative of f with respect to y squared. But in these off diagonals, we have these mixed derivative terms, partial respect to f with respect to x and y, and then with respect to y and x. So that's how we define our Hessian. We can even look at the determinant of that. But anyway, we can take a function and calculate a bunch of partial derivatives and build our Hessian. Revise derivative tests for multiple variables. So here's the derivative test. If our Hessian is greater than 0, and we can look at the second order partial derivative with respect to x or y, if that is less than 0 and the Hessian is greater than 0, then we have a local minimum. Again, if our Hessian is greater than 0 and our second order partial derivative is greater than 0, this is with respect to x, but could also be with respect to y, then we're talking about a local maximum. So that's easy. However, calculating the Hessian is a lot of work. Once we have that, it becomes quite easy to determine whether we have a local minimum or a local maximum. If the determinant of the Hessian is less than 0, that's how we know we have a saddle point. It's only when it's greater than 0 that we know we have an extrema. Conjugate gradients. What we're looking at here is some function and its isocontour lines. Yes, these are perfect circles, but it does not have to be. So what is a conjugate direction? Let's start by picking 2 points, any 2 points, just not the same point. Then what we're going to do is perform one-dimensional optimizations in any direction, but we'll pick the same direction for XA and XB. So they're parallel directions, but we could have chosen any direction. Along those, we will do 1D optimizations, and that will lead to 2 extremas. And we'll label those as X1 and X2. If we draw a line that connects X1 to X2 and we keep going, that is called a conjugate direction. And that conjugate direction is directed towards the extrema, the maximum or minimum. Here's an alternate way to define a conjugate direction. Here we start with a single point, and we do one-dimensional optimizations in 2 different directions from the same starting point. We find the extrema along both those directions, and now if we draw a line through those 2 extrema, that is in the direction of the overall extrema, and that is a conjugate direction. Same conjugate direction we had on the previous slide. So we have 2 ways of constructing a conjugate direction, and this tells us what direction to move in to get to the global extrema. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.